we're going to use implicit differentiation to solve related rate problems. And so we're going to start with this example, and we'll just show a bunch of different examples of related rate problems, and we'll just kind of make them a little more complicated each time. So in this video I'll show a couple, in the next video maybe I'll show a couple, and so on. I'm not sure how many we'll do in all, but hopefully this is enough to help you see what's going on in these problems. Okay, so normally in these problems you're going to be given an equation that's going to relate two or more variables together. So here's an equation relating x and y together. So 3x squared plus 5y is equal to 10. And then what I'm told here is that both of these variables vary over time. So even though we don't know what the function is, there's some function here that relates x to t and that relates y to t. Both of these variables are changing with respect to time, and that's a function. So that's our implicit differentiation, our implicit function that we're going to be using the derivative of. And in this case, we're told that at x equals 2, the dx dt, so the rate of change of the x variable with respect to time, is -7. And so now what I want to know is, what is the rate of change of the y variable at this time? So here's the idea. Here is an equation that relates together two variables. We are also told that both of those variables vary over time. And then given the rate of change of one of the variables at a given time, we're being asked for the rate of change of the other variable at that time. So here's the idea. What I'm going to do is I'm going to take the derivative of both sides of this equation, but I'm going to do it with respect to t. So in other words, I'm going to take d dt of this side, 3x squared plus 5y, and then d dt of 10. So I'm taking the derivative with respect to t. So the bottom here tells you that it's with respect to t. So now I'm going to use implicit differentiation, and I have to use implicit differentiation for the x and the y because it's with respect to t. Okay? So not just for the y, but for the x and the y with respect to t. So I'm going to take the derivative of both of these terms. So for this one, using implicit differentiation, I'm going to treat like what I have here is 3 something squared, and then inside I have an x variable that's like a function of t implicitly. I don't know what that function is, but I'm going to take the derivative of the outside, which would be 6, evaluated at the inside, x, and then I take multiply it by the derivative of the inside, which is dx dt. Okay, and now this one will just be plus 5 dy dt. Okay, and that's implicit differentiation. Both of these with respect to t. Now this is a constant, so if I take the derivative of a constant with respect to t, that's just equal to 0. So I have this equation, and it involves both a dx dt and a dy dt. And so now what I'm going to do here is, I'm told that at x equals 2, dx dt is equal to -7. Okay? And then it wants to know what is the rate of change of dy dt. It says, well, what's the rate of change of y at this time? So the rate of change of y is the dy dt. So what I'm going to do is I'm going to solve this equation for dy dt. And if I do that, I'm going to have 5 dy dt is equal to, and I'm moving this over to the other side, -6x dx dt. And then I'm going to divide both sides by 5. Get rid of that. And then up here, I'm going to have dy dt is equal to -6/5 x dx dt. So this is the derivative of y with respect to t. And notice on this side I have an x and I have a dx dt. Well, that's what I'm given here. I'm given at x equals 2, when x is equal to 2, the dx dt is equal to -7. And so what I'm going to do here is I'm going to plug those in. So this is a -6/5 at 2, so I plug in 2 for the x, and then for dx dt I plug in -7. And so now what I can do is I can calculate the dy dt. So this would be, so -6 times 2 is 12 times -7. 12 times 7 is 70, 84, and the two negatives cancel out, so I get -84/5. Okay, and that would be the dy dt. That's the rate that it's looking for. Okay, so here's the idea. We have an equation, some sort of equation, that relates these two variables together, and both variables are functions, implicit functions of time. They both vary over time, and so I'm given some information about the rate of change of one of the variables, and then what I want to do is I want to find the rate of change of the other variable. So you use the implicit differentiation, and then you can plug in the information you're given and find the rate of change of the other variable. Okay, so now let's actually solve something that'd be like an actual problem. Okay, and so this is about the volume of a balloon. So we're going to assume that the balloon is a sphere, and so the volume of a sphere is 4/3 pi r squared. So this is an equation that relates the volume together with the radius. Okay, and so it tells me here that suppose a pump is pumping air into the balloon at a constant rate of 25 cubic inches per second. Okay, so that's the air. That pump just constantly it's always pumping it in at 25 inches cubed per second. And then it wants to know how fast is the radius of the balloon changing when the radius is 8 inches long. Okay, so notice what they're giving me. They give me an equation here that relates the v and the r together. Okay, and then this is actually dv dt. That this is the amount of volume that gets pumped into the balloon each second, right? And so the dv dt is 25 inches cubed per second. Okay, that is what dv dt is. And it's going to be that, it'll always be that. For every given time, it's going to be 25. It's being pumped in at a constant rate. Okay, then it wants to know when r is 8 inches, it wants you to find the rate of change of the radius, so dr dt. That's what it wants you to find. Okay, so you use this equation, and you're going to use implicit differentiation, differentiating both sides with respect to t, and you're going to plug in the information you get to find dr dt. Okay, so let's see if we can do this. So I'm going to take the derivative with respect to t of both sides of the equation. Okay, so this is just going to be dv dt. Okay, now this is going to be, I'm going to take the derivative of the outside function. So this is like r being inside a square function, right? And so, and the derivative of r is dr dt. So I'm going to take the derivative here of the outside. I'm going to use the implicit differentiation with respect to t. So bring the 2 down, and I get 8/3 pi r, because I bring the 2 down and subtract 1 from the exponent. But then I got to multiply by the derivative of r with respect to t, which is just dr dt. So it looks like that. And now I can solve for dr dt, because that's what I want to find, the rate of change of the radius. And so I just move all this to the other side. So I have like dv dt divided by 8/3 pi times r. And so notice, when r is 8 inches, find dr dt. Well, I know dv dt. They give me that in the problem. That's the rate of change of the volume of the balloon. And then I'm given at r equals 8. So I plug in dv dt, plug in 8 for r, and then I can calculate dr dt, okay? Because these are related rates. This equation also, it relates the r and the v. It also relates the rates of r, dr dt and dv dt. So plugging things in now, it's a constant of 25 inches per second cubed. And then I multiply or divide this by 8/3 pi, and then I have, oh, and you know what? I'm actually made a mistake here. This should be 4/3 pi r cubed for the volume of a balloon. And that being the case, then I'm bringing a 3 down. I'm bringing a 3 down. So this is 12. And then I have a square here. Okay. And so this should be 12. And this would be a square here. Okay. And so this would be 12. And then this would be r squared. So that would be 8 inches, 8 squared. So it would look like this. And you know, the way that I figured this out, the reason I knew I made a mistake is in my mind I was thinking of the units, and I knew this was inches cubed per second, and this was just a regular inch, and so I knew this rate was going to have an inch squared, but it needed to have just an inch, not an inch squared. So I knew this needed to be a square to cancel things out, leaving you with a rate that was just inches per second. And so I knew I was off by a dimension. That's how I caught my mistake. But so now what I can do is I can plug this into my calculator, and I can find the rate of change of the radius. So I have 25 divided by, so this is 12 divided by 3 times pi times 64, 8 squared. All that's on the bottom. And, oops, I needed to divide here. So divided by, okay. And there we go. So what I have here is like 0.031 inches per second. So it's not changing very fast. And so some of this is probably that this rate here is not very much. It must not be putting much air into the balloon. I just made this problem up in my head. And so that must not be putting that much air into the balloon, which causes the rate of change of the radius to not be terribly fast. But that's what it would be. Okay? And that is the idea of a related rate problem. Again, we have an equation that relates two or more variables together. I think most of the ones we have are going to be two variables together. Both of those variables varying with respect to time. And then we're given information about one of the rates, and then we use the implicit differentiation to find the other rate here. In terms of the rate that you're given information about, you plug in the information and you can find the other rate. And so that is the idea behind the related rate problems. Now, the thing that'll make these maybe a little more challenging is we're not going to necessarily be given this. We're going to, in a lot of the problems, we're going to have to find this, right? We're going to have to derive. We're going to have to know some of the, like the formulas for a sphere or the formula for a cone the formula for distance between things, or some trigonometric formula dealing with a triangle maybe. So that's what's going to make these a little bit challenging. We're going to have to set up the problem and then interpret these rates and then plug things in to find the rate that it's asking about.